Hello, this video is going to cover oscillations, or simple harmonic motion. I'll come back to what exactly the term simple harmonic motion means in just a moment after we talk about some motivation for it. So this video will go over the derivation of the formula governing simple harmonic motion. We'll talk about energy for part 2. We'll go over this problem, and then we'll talk about pendula, so the oscillations corresponding to like a pendulum going back and forth. Okay, so let's go into some motivation for this topic. Okay, so if you were to look at a potential energy function for a conservative force, you could get any random shape like this. What we're going to be interested in are oscillations about any stable equilibrium point. So so there are two of them in this problem. Pretend we're just interested in stable motion around this equilibrium point. Okay, so there's another stable equilibrium point here. We're not going to care about that one. So your book has this coordinate x, and x equals 0 is defined to be at the location of the equilibrium point. So I'm going to shift my axis over. I'm going to redefine what we're calling x equals 0 to be right here, because it has to be at the location of the equilibrium point. And this is just to save by so that your book doesn't have to write x minus x naught all the time. So it looks a little cleaner to write it this way. Okay. The function can be approximated with a parabola around that point. That's a funny looking parabola. Imagine that was a perfect parabola that's supposed to match the curvature of this function. So maybe it looks more like this. That's maybe better. So the potential energy function, it's some exact function, which is in black. We can approximate it around the equilibrium point with a parabola. So this parabola, so if we were to approximate the function, to lowest order, it would just be a straight line. But that's not really going to tell us anything about how the potential energy changes. And we're going to see that that's important because that's going to relate to the force. So we want a little bit more information than just a flat line. And then the tangent line is 0. So we need to go to second order in the Taylor expansion for u of x around x equals 0. So it's equal to some constant plus, I'm going to write this as 1/2 kx squared plus higher order terms in x. One explanation for why that 1/2 is there is that, like in the Taylor expansion, it's 1/2, or it's 1 over 2 factorial times the second derivative times x squared. So k is like the second derivative of our potential energy function. But there's an even better explanation. And that has to do with looking at the force associated with this potential energy function. So I'm going to write down f as a function of x, which is minus du dx. So taking minus a derivative of the top expression, that u naught doesn't play into it at all, we get minus kx. So this is Hooke's law. Okay, so either you put the 1/2 here, or you have to have a factor of 2 here. And so so just to be consistent with Hooke's law, so the interpretation of k, in addition to being the second derivative of the potential energy function, it's also the force per unit length exerted by the spring. Or more generally, just whatever object or whatever the interaction is, whatever the potential energy function is. So your book talks a lot about a spring, but this is more general than that. Okay, the more I look at this parabola, the less I like it. Let me try it one more time. I keep trying to avoid that. There we go. It's okay if it matches the black one for a while. That one looks better. Yeah, I'll take that one. Okay. So the goal of what we're trying to describe is the motion. So key in on the word simple harmonic motion. We want to know the motion, the x of t, x as a function of time, for an object that's displaced from equilibrium. So imagine you took a block connected to a spring and you displace it from its equilibrium value and you let it go. It's going to oscillate back and forth. And so we can pretty quickly show what the motion is going to look like. Okay. And to do that, we use Newton's second law. So the force, we're going to assume the only force acting on the object is the force associated with this potential energy function, or in other words, just the spring force is the net force. Okay, so we're assuming right off the bat that there's no friction, right? There's no non-conservative forces here. So the force is ma, or 2 derivatives of x with respect to time. And remember, x is a function of time. So whether I write x or x of t, it doesn't matter. Okay, so I'm going to go back and forth writing the two. So F equals ma, and we're going to use the fact that we can relate this to some property of the curvature. So this is minus kx. Or in other words, 2 derivatives of this function, x of t, with respect to time, is equal to a minus a constant. I'm gonna move the mass over to the other side at this point. Yeah. Minus k over m times x. So 2 derivatives of a function is minus a constant times x of t. So we're going to replace k over m with this new thing called, omega is square root of k over m. So this equation becomes, and like I said before, we can go back and forth. X and x of t are the same thing. So 2 derivatives of x is minus a constant squared times the function again. So we have to think about what function can we take 2 derivatives of and we get minus the function back. And the answer to this is that it's a sine or a cosine. So this is a second order ordinary differential equation. There are 2 solutions. So we could have a cosine. So I'm going to call this lowercase a for a second. You'll see why. We're going to rewrite this another way. So you could have a constant times cosine omega t, or you could have a constant times sine omega t. And the general solution is the addition of the 2. Okay, so try just x is equal to this function, or just x is equal to this function, and no matter what the value of a or b is, either one will satisfy this differential equation. So keep in mind that for each time you take the derivative with respect to time, because of the chain rule, you get a factor of omega. So 2 derivatives, you get 2 factors of omega. And that's what motivates this definition as square root of k over m, because it's after applying the chain rule twice that you get this factor of k over m. Now your book, if you've taken a look at your book doesn't write the 2 parameters as the thing multiplying the cosine and the thing multiplying the sine. Your book writes it this way. So it's completely equivalent to have your 2 constants of integration. So another thing, you can think of a and b as 2 constants of integration when you integrate this second derivative. Another way that you can write the solution is just as a cosine, but you allow for a phase constant. Okay, so instead of lowercase a and lowercase b, we have the amplitude of motion, and then just a phase, which depends on where you're calling t equals 0. So where in the oscillatory motion are you calling t equals 0? And most textbooks prefer this form, including yours. Yeah. So you could have chosen either one of these. Now the solution to this differential equation, so it's for any stable equilibrium, you can approximate it with a parabola. It has this sinusoidal solution. The motion is called simple harmonic motion. So this is where the term comes from, simple harmonic motion. It refers to this particular setup, but it's more general than just springs. Okay. Okay, so now some terminology. So omega is the angular frequency. Omega is angular frequency. It's the number of radians per second that your object is undergoing. So this object is going back and forth between, so there's an equilibrium position, there's x equals a and x equals minus a. X equals minus a, x equals plus a, and say your object starts here. So your object just keeps bouncing back and forth between these two. So it starts off slow, it moves faster and faster, and then slows down, and then it goes back again, faster and faster, and then slows down, and it keeps going back and forth. Now, the overall phase, what's in here, and it's easiest to think about this, imagining the particle starts off at x equals a. So in other words, the phase constant phi is 0, if that's where the particle is at t equals 0. Now, where you are in this journey, from here and then back again, that's a certain number of radians. So 2 pi is the number of radians to get all the way back. So omega is the number of radians per second. So it's saying how quickly this motion happens. So you have angular frequency, you have frequency, which is just omega over 2 pi, or natural frequency. And then you also have period, which is 1 over f, or 2 pi over omega. This is called the period of motion. So natural frequency is in cycles per second. It's saying how many times you go back and forth in 1 second. And then the period is how long does it take for one of these cycles. So how long would you have to wait for this particle to get back to the amplitude A? Okay. Other things here are A is the amplitude. It's how far. So in one whole oscillation, how far away does the mass get from equilibrium? That's the amplitude. And phi would be the phase constant. So this corresponds to, like, when t equals 0, where is it along this journey? Because you could say t equals 0 when the particle is this, right here and moving to the right. So if the particle is at x equals 0 at t equals 0 with some non-zero speed, then phi would either be plus or minus pi over 4. I'm sorry, plus or minus pi over 2, a quarter of a cycle. Okay, I think that's all of the parameters introduced, all of the names. Okay, so we're almost in a position where we can do this problem, but we need to talk about energy first. So like I said before, there are no non-conservative forces here. So in simple harmonic motion, we haven't included what's called a damping term. Your book covers this later in a later section, how to deal with damping. So we're not going to talk about that in this course, but you'll see it in a course very soon. So we're not going to talk about dampings, and because there's no non-conservative forces, the total mechanical energy is constant. Total mechanical energy is U plus K, the kinetic energy plus the kinetic energy, potential plus kinetic. Now we know that this is going to be constant, but we can actually show that it's constant and get a little bit more information about what's going on. So to do that, I'm going to write down, remember our potential energy function is this. We're approximating the actual potential energy function with the blue U of x, which is this. And we saw that U naught doesn't really affect anything, right? It never came up after, so we took a derivative for Hooke's law and it never came up again, right? So we're just going to set U naught equal to 0. So our potential energy is going to be 1/2 kx squared. And remember, x is a function of time. So 1/2 kx squared, but x is a function of time. And the kinetic energy is 1/2 mv squared, and v is a function of time. So I'm going to plug in the x of t that we have shown for simple harmonic motion. I'm going to plug this in. But for v, what I should plug in is related to this. So I'm going to take a derivative of this with respect to time to get the velocity function. So v is the derivative with respect to time of x of t, or the derivative with respect to time of a cosine omega t plus phi. So from the chain rule, we get a factor of omega, and the derivative of cosine is minus sine. So we get this is the velocity as a function of time. Okay, so plugging this back into our total energy equation, we get 1/2 k x squared. It's a cosine, and I'm just going to write, so this omega t plus phi, I'm just going to write dot 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 for that. But every time I write dot 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 in parentheses, it's omega t plus phi. Okay, so that's the potential energy, and then 1/2 mv squared. This is minus a omega sine squared. So this is 1/2 k a squared cosine squared plus 1/2 m omega squared a squared sine squared. Now, this right here, remember that omega was square root of k over m. So if I square both sides of this relationship, and I multiply by m, I get k is equal to m omega squared. So for m omega squared, I can plug in that is equal to k. And so E total is 1/2 ka squared, which is common to both of these two terms, cosine squared plus sine squared. And now what's in here depends on time, but it's the same exact thing for both of these. So cosine squared of whatever that quantity is plus sine squared of that exact same quantity is equal to 1. And so the total mechanical energy is 1/2 k times a squared. So the amplitude is constant. Even though the x value of motion is changing, the amplitude is constant. So we already had a suspicion that the total mechanical energy was conserved, but we've derived exactly what the value is of that. So this mechanical energy is conserved. And it makes sense that it's equal to the initial potential energy if the particle starts off at x equals a. So as the thing speeds up, the potential energy goes down, the kinetic energy goes up. So the energy is just bouncing back and forth between potential and kinetic energy. Okay, so we are in a position to answer this question. And immediately, if you're given k and m and you're asked something about the period of motion or anything related to frequency, you have to remember this relationship omega is square root of k over m. So k over m is 200 divided by 0.5. So it's square root of 400 in SI units, or 20. So this is 20 radians per second. So the period of oscillations is going to be pretty easy if we have omega. So omega is 20. So we're doing the original problem now. Omega is 20 radians per second, which means that t is 2 pi over omega. Let's see, 2 pi over 20, a tenth of pi. Looks like that's 0.31 seconds. Right? 3.14 is pi divided by 10. So scoot the decimal over, and then this is all in SI units, so period is in seconds. Okay, so pretty fast. So like now. That's about a third of a second. Pretty fast oscillations. All right. B. How long does it take for the object to get from its initial position? So let me draw. So imagine the block is, imagine the equilibrium position is right here. Yeah. So imagine this is t equals 0 in this picture right here. And this is the equilibrium position right here, x equals 0, and then this right here is x equals a. So the block starts off at its maximum amplitude, It goes here after some amount of time. Eventually it goes down to minus a, and then back in the positive direction. So how long does that take? If it takes one whole period, capital T, to get from here, 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 and then back again, how long does it take to get to equilibrium? It's 1/4 of that, right? A fourth of the time to get to minus a fourth of the time, a fourth of the time. So this picture right here, for the block to get in equilibrium, this takes 1/4 of a period to get to there. So keep in mind, the word equilibrium doesn't mean the object's at rest. So the main way to get confused with part B is equilibrium means no net force. And from Hooke's law, if F equals minus kx, that means x equals 0. And if x equals 0, there's no potential energy, but all the energy is kinetic, so the object is still moving. So this is just another warning that equilibrium means no net force, but the object can move. So the answer for this one is 1/4 of a period, 1/4 of 0.31 seconds. And I think this was 0.079 seconds. Part C, what is the maximum speed of the object? What is the max speed of the block? Now for this, we can do this two different ways. So the first way is that we can compute the total energy and then set that energy equal to 1/2 mv squared. So E total is 1/2 ka squared. So this is 1/2, the value of k was 200 newtons per meter. And the amplitude, so this depends, so now this is a piece of information that we haven't needed for parts A and B. The amplitude is 5 centimeters. And I probably should have said this before, but what's interesting about the period is that it doesn't depend on the period, the period, this omega, doesn't depend on the amplitude at all. So in other words, if I take a particle and I scoot it over 1 centimeter and release it from rest, it'll go back and forth. If I scoot it over 2 centimeters and then release it from rest, it takes the same amount of time. Even though it's covering twice as much distance, it takes just as long. So that's counterintuitive. And the reason for that is that the force is bigger, so it accelerates more, and it's moving faster on average. So it's able to cover twice as much distance in the same amount of time. So, so parts A and B didn't depend on the fact that it was 5 centimeters at all, but for the energy, how much energy the block has, how fast it's moving, that does depend on how far away from equilibrium it started. So at this point, we need 5 centimeters. So this is 0.05 meters squared. So multiplying this out, 100 times 1/20 squared is 1/4, or 0.25 joules. So then we would, so the maximum speed is when the total energy is all kinetic. So the maximum speed is when the whole energy is kinetic, so we can set V equal to V max. So 0.25 joules is 1/2 times, the mass was 0.5 kilograms. So look at that, 0.25 and a 0.25. So it looks like V max is 1 meter per second. Okay, that was one way of doing it. A more straightforward way of doing it would have been to use this function right here. So V of t oscillates just in the same way that the position oscillates. So if you look at what's in front of the sign, you have minus something times sign. The amplitude, well, I shouldn't say amplitude, but the thing in front of the sign is a omega. And so the biggest value, the biggest absolute value that V can have is a times omega. So in general, V max is equal to A times omega. And if we look at 0.05 meters, remember we displaced, the amplitude was 5 centimeters, and our omega was, do we have it for this problem? 20 radians per second. Looks like 1/20th times 20 is 1. This is 1.0 meter per second. It's the same thing. It's not necessarily, like, this isn't an equation you would really want to memorize, but it does come out of what you should memorize is this, the equation for simple harmonic motion. And then when you take a derivative, you just get another factor of omega from the chain rule. Okay, so it's pretty easy to rederive, if you will. Okay, this is the gist of what your book goes over the whole section. So it gives a quick example of it, same thing. And this information about the energy and how the sine squared plus cosine squared equals 1 means that the total mechanical energy is constant. So for some reason, your book doesn't give this a section number like it does for every other chapter. So this is just 17.0. Okay, one last thing is oscillations for a pendulum. So both of these, so what we just did with simple harmonic motion, so this discussion was completely general. A pendulum is a particular setup, so a particular example of simple harmonic motion. So your book talks about any random shape being hung from some pivot point that's allowed to rock back and forth. And your textbook derives an equation for the angular speed, the angular frequency of oscillations. Depends on this parameter kappa and the moment of inertia about the pivot point. So this is a general pendulum. We're just going to worry about a simple pendulum. So in other words, we have a string of mass L, and your book calls this lowercase l, and then just all the mass is just at the end. So this moment of inertia would be ml squared. So we have just m that is displaced some angle. Okay, so with this particular pendulum, this is called a simple pendulum. Now, the gravitational force is actually pointing down. So if we look at a free body diagram for this mass, there is a force down, mg, and then there's a tension this way. The tension, so remember also, for something undergoing circular motion, a good coordinate system is towards the center, like it's basically in the same direction as the tension, not the gravitational force. Because the string is preventing any motion in the radial direction, but there can be an acceleration in the tangential direction. Okay, so in other words, a nice thing to do is to split gravity into the component that's tangent to the motion and then perpendicular. So tension is just canceling one of those components of gravity, but the mg sine theta is not canceled by the tension. So what I'm trying to say here is that the net force on the pendulum is mg sine theta. And it's so this is the force on the bob. And now, so the way I've talked about theta, I've introduced theta, is that this is the direction of increasing theta. And the force is opposite that direction. So really, with theta defined to be positive, the more the pendulum gets away from equilibrium, the force is in the negative direction. So F equals ma, the acceleration of the bob. I'm going to swap sides here. So MA, and instead of A, I'm going to do R times alpha. From rotational quantities, we can do that. Equals minus mg. And at this point, I'm going to do the small angle approximation. Well, yeah, that's fine. So at this point, I'm doing sine theta. This is why we talked about the Taylor series in the previous video. Sine theta is approximately equal to theta. So we're going to derive a formula that works for small angles. But it winds up being pretty accurate to 10 degrees, 20 degrees. So it might seem like too special of a case, but it works really well. So we can divide both sides by m and divide by L. So we have minus g over L theta equals 2 derivatives of theta with respect to time. So this is the key differential equation for a pendulum. You're going to see this a lot. So this is the second example that you've seen just in this video. You have 2 derivatives of a function is minus something times that function again. The answer, so 2 derivatives with respect to time is minus something times that function. The answer is sines and cosines, and the angular frequency is always the square root of this thing. So it's minus some constant times the function again. So omega, we're going to define to be square root of g over L. And the answer for theta equals some initial angle, so theta initial, cosine, or I'll call it theta max, this is the amplitude, cosine of omega t plus phi naught. So the function, that's nice and all, but this is really the key. This is what is some useful information here. This tells us the angular frequency of oscillations of a simple pendulum. And notice how it doesn't depend on theta max. Just like before with simple harmonic motion, it didn't depend on the amplitude. Similarly here, the period or the frequency, so some related formulas here. F is omega over 2 pi, or 1 over 2 pi square root of g over L. That's how many cycles per second, or the period of a pendulum is 2 pi square root of L over g. So g is 9.8 meters per second squared on the Earth. And this only depends on the length of the pendulum. The longer the pendulum, the longer the period. So you've probably noticed this before. Hang something that's pretty short, look at the period of oscillations, do something a lot longer with a lot longer of a string, it's going to take longer to oscillate. And release it from a small angle, measure how long it takes and compare with this formula. You'll find that it's pretty close. 10 degrees or 20 degrees or 30 degrees, you're going to get just maybe a couple % error. Yeah, that's the gist of this section. And then later on, it introduces damping, but it requires a little bit of detail to go into that. Okay.